Okay. So these are the type of skills in this starter question that you need to know or be aware of, be pretty familiar with in order to do well with section 5.4 on polynomial and rational inequalities. Inequalities, as usual, are a little bit more difficult than equations are, but I think by the time we get done, you'll have enough skills and a little set of tools that you can use to make these relatively easy. So if you had a choice between graphing either the first one, f of x equals that polynomial that's already been factored, or b, that rational function that's already factored, which one would you rather do, a or b? A is a lot easier, right? Crosses at 1, crosses at -2, crosses at +3. Looks like x cubed. Okay, we're familiar with all of that behavior. This one here is a little bit more difficult. You'd have to figure out what the horizontal or oblique asymptote is. You'd have to figure out, are there domain issues? Do they cancel, in which case they become a whole? Do they stick around, in which case they'd be a vertical asymptote? Maybe find some intercepts and stuff like that. That would be like what we did in 5.3 and 5.2. Okay, so a little more difficult. So this one by far is easier. Okay, and if we were asked to solve these two inequalities here, both of them hopefully are pretty easy. These are both linear inequalities. So we'd solve them just like we would solve a linear equation, except for when we do what? Okay, there's what we're looking for. Multiply or divide by a negative. If you multiply or divide by a negative, you have to switch the direction of the inequality. So if I'm solving this one right here, the first thing that I'd want to do is I'd want to add 4 to both sides. Adding anything doesn't change the direction of the inequality, so that stays a greater than. Again, we're reading from the left side to the right side. This side's a 14. I'm going to divide by a 2. Dividing, as long as I divide by a positive, doesn't change the direction of the inequality, so I get x is greater than 7. Now, I could graph that. I could write it in interval notation, but for the time being, that's perfectly okay right there. And then if I were solving this one, the first thing I'd do is I'd subtract 1. Subtracting doesn't change the direction of the inequality, so I'm going to leave that as a less than or equal to, and then I get a 4 over here. And then to get the x completely by itself, I'm going to multiply both sides by -6. So that's going to give me an x and a -24. And when I multiply both sides by a negative, I have to switch the direction of the inequality. So that becomes an x greater than or equal to -24. Okay, that's how to solve those. Those ring a bell, right? Pretty easy? Wish the whole assignment were like this? Okay, we can almost make it so it's that way. Okay, we can almost make it so it's that easy. So if you'll remember from section 4.5, and I'm hoping you do because this stuff comes around again, it'll come up again on the final. If we were to say f of x is greater than 0, it means f of x is positive, and that means the graph is above the x-axis, right? So you can say that in terms of the inequality, we can write it this way. We can think of, oh, well, that just means it needs to be positive. And if we were to graph this, we're talking about f of x's or the y's that are greater than 0. So that means they're above the x-axis. If we say it's less than 0, that means it's negative. Or f of x is below the x-axis if we were to look at a graph. And if we were to say f of x equals 0, then f of x is 0. Or it means f of x is on the x-axis. So if you keep those things in mind, we can actually turn some problems in this section that are really complicated, really pretty ugly, and we can make them pretty easy to deal with. So in 5.4, we're going to deal with rational and polynomial inequalities. And as usual, when we solve something that's a little bit more complicated than just a regular old linear equation, it's going to be better if we compare the equation to 0, okay? Because then we can use the 0 property of multiplication, or graphically we compare it to the x-axis. We just need to know whether it's above or below or on the x-axis. Okay, so we're going to do a couple of examples, and I want you to take a look at these first two examples. One of them is 1, the other one is 1 star. You'll notice that they're set up just a little bit differently. Just the instructions are a little bit different. So I'm going to I'm going to show you the way that I think you ought to solve these in general. Okay? So if you're asked to do these, I'm going to show you a technique that I think works the best. So if I were going to do this one right here, what I would do is I would think, well, wait a minute. I know how to graph this. This has an x-intercept at 1, at -2, and at 3. The multiplicity on every single one of them is odd, so it crosses each time, and it looks like, double check and make sure, that's a plain old x, plain old x, plain old x. So it does look like positive x cubed. Now, it doesn't have to look perfect, so I'm going to put -2 here, I'm going to put +1 here, and I'm going to put +3 here. If you want to put a y-axis on there, go right ahead. If you want to find the y-intercept, that would be fine. But all I need to be aware of is it looks like x cubed. So that means it starts down here and ends up there. How many turning points can it have? Up to 2. So let's make it start here, crosses through here. It's got to cross through this one right here, right? Cross through that, and then cross through that. Okay, that's what the graph looks like, right? Really easy, decent review of some skills that we already know how to do. Okay, we want to know where this is less than or equal to 0. So if this were f of x, we'd want to know where it's less than or equal to 0. Well, what does that mean? That means below or on the x-axis. So the portion of the graph that we'd be describing is this portion here and this portion here. Now, does it include this point right here? Yes, it does. And this one, because we're asking where is this on or below the x-axis, right? So the part of the x-axis where this would be true is here and here. So let's write the answer in interval notation. It would start at -infinity. It would stop at -2. Now always round around infinity. What about the 2? That's going to be a square because it can actually equal that. And then we stop for a minute and then we start up again at 1, and that's going to be a square bracket because it can actually be on the x-axis. And then we're going to stop at 3. Any questions there? Okay, that's the answer. That's it. Okay. You can also use something called a sign line in order to figure these out. Now, sign lines are fairly useful, so I am going to show you how to use this. But in general, it's probably going to be better if you do it using this other technique. Okay. So what we do is we factor the polynomial, set it equal to 0, or compare it to 0. Factor the polynomial, and then what we do is we use each 0 to separate the x-axis into little intervals. And then once we separate it into little intervals, we're going to pick a number, any number you want. We'll call it a test number. Pick a number in that interval, and we're going to see whether it's above or below the x-axis. Okay? If the result is positive, the function is greater than 0. Okay? I'll put greater. Okay? And if the result is negative, then the function is less than 0. So here's the x-axis. Notice this didn't really say, I mean, if you look at it, it doesn't really have any f of x's or any y's or anything like that. Okay? So all we're doing is we're saying, look, right here the 0 is 1. So let's put 1 on the x-axis, or on this number line. The 0 here is -2, so here's -2. And the 0 here is +3, so here's +3. So what this has done is it's broken up the x-axis into 4 different little intervals. There's one here, one here, one here, and one here. Now, if you want to check and see what the sign of the function is, or the value of this expression is, we just pick any point we want that's in that interval. So if I had to pick a point in between -infinity and -2, what point do you want to pick? -3 works, -10. I mean, don't pick anything too terribly large. And here's what we're going to keep track of. The number I'm going to choose, and I'm going to change colors for this, is I'm going to choose -5. I'm going to choose -5. Now, if I plug in a -5, remember, we don't really care what the number is, we just care what the sign is. So if I plug in a -5 into this, what's -5 minus 1? -6. So that first factor is negative. Now, it happens to be -6, I'm really concerned with the fact that it's negative. What if I plug in a -5 here? Okay, that's going to be -3, but I'm really concerned that it's negative. Plug in a -5 here. Okay. What's a negative times a negative times a negative? Okay, so that's negative. And right here, it's 0. Right at -2. If you plugged in a -2, the whole thing, this factor is 0, so the whole thing would be 0. Okay? Now we want to know where this is less than 0. We want to know where it's negative. So would this work? The answer here would be yes, it would work there. Okay, if you wanted to pick somewhere in between -2 and 1, what would you pick? Probably 0. So let's plug in a 0. If I plug in a 0, what's the sign for this first factor? It's going to be negative. What's the sign for this one? Positive and negative, right? Two negatives make a positive. So this is positive right here. We don't want it to be positive. We want it to be less than 0. We want it to be negative. So does that work right there? Answer there is no. Can you see why we call this a sign line? Because all we're interested in is the sign of each one of those factors and the sign of the result once we multiply them together. Now, if I were to pick a point over here, let's say we pick x equals 2. That's going to be positive. That's going to be positive. That's going to be negative. So what's our end result? End result is negative. Okay? So does that work? Yes, it does. And if you were to plug in here, say we picked x equals positive 10, and we went through, this would be positive, this would be positive, this would be positive. So our end result is positive. That's not what we want. We want our answer to be less than or equal to 0. We want it to be negative or 0. So the answer here is no. So the only interval that works is, again, -infinity to -2. Do we include the -2? Yeah, because it can actually equal 0. So we'd include that. And then we start up again at, start up again at 1 and go to +3. There's the answer. Now, which do you like better? Do you like drawing the picture or do you like doing a sign line? Picture's probably a lot better, isn't it? Okay? But this is a polynomial. Polynomials are easy to graph. If it were a rational equation or a rational function, it's a little bit more difficult, but I'll show you how to deal with that. Okay. So we like the graphing technique a little bit better, am I right? Okay, so let's take a look at example number 2. It says, solve the inequality 3x cubed greater than 9x squared. Okay, what's that?
It's not set equal to 0.
Okay, the key here is it's not set equal to 0. Now just watch, don't write this down. A lot of people will look at this and they'll say, hey, wait a minute, can't I just divide both sides by x squared and get this? And then start dividing by 3 and get x is greater than 3 and solve it that way? You could try, but you're usually not going to get a complete answer. Okay, the minute you divide both sides by that x squared, when it cancels off, might take some answers with it. So you want to be really careful when you're doing something like that. Again, it's going to be a lot better if we compare these to 0. So the first thing I'm going to do is I'm going to move that over. So this is going to be 3x cubed minus 9x squared greater than 0. Now, this is still a polynomial. It's like 3x cubed. It's a third degree polynomial. It's been multiplied by 3. Okay, but we don't know where the zeros are, and we don't know whether they touch or cross there and things like that. We need to know more about this shape. So what do we need to do with this? Factor it. So I'm going to take out a 3 and an x squared, thank you. I'm left with an x minus 3. So what's the 0 from here? And its multiplicity? Careful, 2. So it's going to touch. And here? 3. Its multiplicity? 1. So it's going to cross. Okay, so I'm going to draw a little sketch right here. And again, the cool part about this is your sketches don't have to be perfect. The most important thing is Do they have the right behavior at the x-intercepts? So did you get the right intercepts, and did you make it touch and cross? And can you tell whether it's above or below there? So it needs to hit 0, and it needs to hit at 3. What does it look like? 3x to the third, but really x to the third is the big deal. Does it start up here or down here? Starts down here. Now, when it gets to 0, does it cross through or does it touch? Touches. And when it gets to 3, cross through or touch? Cross through. So this is what it looks like, right? Okay, now I'm going to change colors again. Let's look right here. We want to know where this graph is greater than 0. What does that mean? Above the x-axis. That's just this piece right here, right? So what's the answer? 3 to infinity, round or square? Okay, it is going to be round. Now, is this point right here included? No, because that would be on the x-axis. And how about this one right here? Not on that one either, okay? Good? There's the answer. Now, if you had to write it in, yeah.
When we solved it the other way, divided and did all that stuff, it was the same thing.
It was. You're right.
So why couldn't we do that?
Very good. Look at the next question. If we had done it that way, correct me if I'm wrong, but before we got this, right? And if we did that same technique here, we'd get x is greater than or equal to 3, right? Okay. So if we relied on this picture and we just said, hey, or we relied on not the picture, but just doing it this way, we'd say x is greater than or equal to 3. Would that be the entire answer?
No.
It wouldn't, because it doesn't include 0. Okay. The answer that we're looking for on this one right here is where is it greater than, where is it above the x-axis, and where is it on? It's on the x-axis here and from here forward. So the answer to this one is going to be 0 union, whoops, square bracket, 3 to infinity. Okay? So to answer your question, Tylin, if we divided by x squared, on that particular one, this one right here, you don't lose any answers, but you would lose some answers right here. Does that make sense? And this is just a simple example. It can get much worse than that. If you start canceling things off before you should, or don't take into account the answers that it would have produced. Okay, are there any questions? Okay, all right. Okay, the previous page had all polynomials on them, and those are pretty easy to graph. We don't have any domain issues or anything like that. Take a look at this next one. Technically, I suppose this would be a rational inequality. Are there any domain issues?
No.
No, nothing weird we need to be aware of or anything like that. In fact, I could just pull this out front and think of this as a 1/2, and then this would look like 1/2 x squared. You with me there? Okay. In fact, let's do that. Do you know what this looks like? Looks like 1/2 x squared, right? It looks like a parabola. Opens up, right? So this is like 1/2 x squared. Now, the big deal is not the 1/2, it's the x squared, because we know x squared is going to look something like this. It's going to be a parabola. What's the x-intercept? 3. What's the x-intercept? -2. We're interested in where this graph is. What does less than or equal to 0 mean? Okay, it means below or on. The less than means below. The equal to means on. So if I were to graph this, this crosses at -2, +3, and goes something like this. Now, do I really care what the y-intercept is or how accurate that graph is? Not a bit. Don't care at all. I only care about where is this graph less than or equal to the x-axis, below the x-axis or on the x-axis. So that's going to be from here all the way over to there. So the answer is negative 2 all the way to 3. Round or square? Square brackets. Okay? If we were asked to write this in set builder notation, which I don't think they ask you to very often, it would be this. It would be x's that are greater than or equal to negative 2 and at the same time less than or equal to 3. Okay, again, I like interval notation a lot better. Okay, I think it makes more sense. But if you had to write it as an inequality, that's what it would look like. Okay, any questions? Okay, now we're going to do something a lot more interesting. Okay, how do you solve inequalities? No, just in general, how do we solve inequalities? What's that? Yeah, you get x on its own, but that's just like we do with anything else. You do it like you do an equation, right? You treat it just as if it were an equation, except for when? If you multiply or divide by a negative. So everything is the same on an inequality as it is on an equation, except for if you multiply or divide by a negative. You've got to keep track of whether or not you have to switch this. Now I want you to watch, please. Don't write anything down. Need everybody's attention up here. Let's say I didn't want to deal with this. I didn't want the 2 there. Is it okay for me to do this? Can I multiply both sides of that by 2? Yes, I can. If I multiply both sides of that by 2, I get this. I get x minus 3. I get x plus 2. Now, correct me if I'm wrong, but multiplying 0 by 2 still gives me 0, right? So don't I still have the same x-intercepts? Isn't this the same direction? Wouldn't I have pretty much the same graph and the same part would be below the x-axis, right? Now, listen very carefully. This is okay because what I multiplied by was a positive number. What if it had been negative? Then I would have had to switch the direction of the inequality. You with me? Yes, it does. Because if you flip it upside down, if you multiplied it by a negative, it would look like this. Okay?
If you flipped it upside down, then it would be like what's greater than or equal to, which would still be negative 3 to 2, so it's still the same answer.
Right. Okay?
Does it really matter?
Yes, it does. It does. I'm glad you're thinking. Take a look at the next one. Can you do the same thing on this one? Why not? You don't know if it's a negative or positive. That's why. Okay? So if you know what the number is, whether it's positive or negative, you know if you have to switch it. That's not the case on this one. It's just an x. X can be any number. Careful here. X can be any number except for 0. So take a look at this one. This is the first one where we've run across where, hey, you know what? X had better not equal 0. I know I have a domain issue. I better make sure that that is not included in the answers. Let me say that again. If you've got a rational expression with a variable in the denominator, there's going to be at least one number that you're going to have to throw out. In this case, we better make sure that our answer doesn't include 0. You with me? How are we doing, McKay?
A little tired, but good.
All right. So, it would be really nice if I could get away without graphing a rational inequality, without graphing a rational function, period. Because I know how to graph this. I know you know how to graph this. By the way, it would have an oblique asymptote, and it would have a vertical asymptote. No horizontal asymptote, though. Okay? If asked to figure that out, you should be able to graph this one. So here's what we're going to do. How can I get rid of that denominator if I don't know whether it's positive or negative, and I don't know whether I should switch the direction of the inequality? We can. What?
Pull it out like how you did with the 2 and 1/2.
Pull the 1/2 out there, but then it's still a rational expression. Zach?
Would you would you do something where if like you're taking the square root, you flip the sign, but you have 2 answers?
I mean, you're maybe a third of the way there. Yeah.
Would you pretend it can be both so you'd have 2 different equations where one's for
You could do that, but that's kind of what he was talking about. Any ideas? What's that? You could try that, but that would be an ugly mess. I'm hoping somebody can get this if I give you a few hints. Okay, here's the problem. I don't like graphing rational functions. Did you have fun on Friday?
No.
Okay. I don't like graphing rational functions. They're not that bad. If I was paid enough money, hey, I can do them all day long. Okay? But in and of themselves, just for fun, it's not really enjoyable. Okay? I like being smart. I like knowing how to do difficult things, but that's not really fun. So if I can get rid of that denominator, I like graphing polynomials. Those actually can be kind of fun because they're pretty darn easy. Okay? I want to get rid of an x in the denominator. So I want to multiply by something that will cancel off an x. But I have to make sure that it's positive. So can I multiply by something that will cancel off an x, but I'm guaranteed that what I'm multiplying by is positive, so I know I don't have to switch the direction. Tylin. Another x. So if I multiplied by how many x's?
Squared. If you times the x by another x, it's going to be x squared.
Right.
So you times by x squared.
If I multiply both sides by x squared, will that cancel off an x?
Yes.
Yes, it will. Is it positive?
Yes.
Yes, it is. Do I need to switch the direction?
Nope.
Nope. Pretty clever trick, isn't it? It's just math. It's keeping in mind that we need to obey, I think you probably learned the golden rule of algebra. Whatever you do to one side, you have to do to the other. And knowing that if we don't want to switch the direction of the inequality, that's fine. You better just make sure you're multiplying by something that's positive. So, is x squared positive? Yes, so I don't have to switch it. And will x squared cancel off an x? Yes, it will. So, what I get is x times x minus 3 times x plus 2, whoops, other way, less than or equal to 0. Isn't this a problem like on the front side?
Yes, but there's one problem.
What's one problem?
One of the factors won't work.
What do you mean?
The x. Yeah, it turned into 0. That's what
Chill out. Just calm down. We'll get there. We'll
Might
get
be
there.
ahead.
Do you know how to graph this?
Yes.
What does it look like? Like x to the third. What's the 0? 0, 3, and negative 2. Now, every one of those has a multiplicity that's 1, so it's odd, so it crosses, right? So here's 0, here's negative 2, and here's 3. Start up or start down? Down. Cross, cross, cross. Now, we want to know where this is less than or equal to 0. So we want to know where it's below, right? So where it would be below is here and here. Now, when we say where, we're asking a question about the x's. So let's give that answer in terms of x's. So that would be from negative infinity all the way to negative 2. Can it equal 2? Yes, it can. So we're going to have a square bracket there. Okay, union, where do we start up again? 0, and where do we stop? Stop at 3. Square bracket around here. What about the 0? Okay, if it were just this one right here, because yeah, that's on the x-axis, that's on the x-axis, we'd include all 3 of them. But remember, we figured out we had a domain issue from the get-go, and we said, there's no way 0 can be part of the answer, so I'm going to do it like this. That is it. So what we've done here is we've changed from graphing a rational function, one with vertical asymptotes and horizontal asymptotes and holes and all sorts of weird stuff like that, to graphing a very easy polynomial function, and all we need to do is keep in mind, hey, are there any numbers that I need to throw out here? You with me? Is that relatively easy? Okay, let's take a look at the next one then. Tylin, what are we going to multiply by? X plus 3 squared. So if I multiply by x plus 3 squared, I'm multiplying by a positive. I don't have to change the direction. And it will cancel with one of those, so I'm left with x plus 3 and x minus 4 less than 0. You're right. Trying to trip you up. Okay. What does this look like? parabola, right? So it's like x squared, so it looks something like this. And we want to know where this is. Below. So where is it below? Negative 3 to 4. And we're going to have this. Now, Zach said, hey, we didn't figure out the domain issue. And it's a really good idea to figure that out first. I didn't do that first on this one. What is the number that we can't include no matter what? Negative 3. Did we include that here? Okay, so whenever you have, again, these are called strict inequalities, strictly less than, strictly greater than, doesn't have the equal to, okay, then that's not as big a deal because you're not going to put square brackets around them anyway, okay? But it is a good habit to be in. Check the domain. Make sure you don't include that. On this one, it didn't matter. On the previous one, it would have been a big deal. Listen up. It would have been a big deal if you had put a square bracket around that. If there's a problem like this on the final exam, you can be almost guaranteed it would be something like this, and it might be a multiple choice, and that's choice A, and choice B is exactly the same, except for they did this. And you'd have to know, hey, wait a minute, I can't include 0. That's not in the domain. You'd have to know that that's not the right answer. Okay? So please make sure you pay attention to that. Any questions? Is this pretty easy? Not quite fun yet, but relatively easy. Okay, let's take a look at the next one. This is problem number 27. What's wrong with it? Not factored. Is it easily factored? You bet it is. Again, all those factoring skills that you learned in Algebra 2, that you practiced in 1010, that we've reviewed to some extent in here, they come in really handy. If you can't factor, it makes this stuff really difficult to do. Let's see, I'm going to have a positive 3 and a negative 1. Is that correct? Any domain issues here? None. And when I graph this, I'm looking for where this graph is above. So this is 0, this is negative 3, and this is 1. So here's 0, negative 3, and positive 1. And it looks like x cubed, so it starts down here. You'll notice that they try not to make things too horrible. Below is this piece and this piece.
Wait.
What?
One's above.
Oh, it does one above. Thanks.
But you don't need to do that now because now the blue's the one.
You're right.
It's okay.
Other than that bugs me. So above is here and here. Okay? So our answers? Negative 3 to 0, round on both. Union. 1 to infinity, sleepyhead. There you go. Okay. Any questions? Sure? Okay. Then let's take a look at the last two on here because they're a little bit different. McKay, what's wrong with 40?
It's not set equal to 0.
Okay, so the first thing we want to do, we always want to compare to 0. That's always going to make our life a little bit easier. So this is going to be x plus 2, x minus 4, minus 1, still greater than or equal to 0. Next. When we were solving these up here, this was a single rational expression compared to 0. Now I've got a rational expression minus 1 compared to 0. I need to make this one single rational expression. In other words, I need to combine these fractions. How do I do that? Okay, careful. I need to get a common denominator first. Okay, so I'm going to have x plus 2 over x minus 4 minus x minus 4 over x minus 4. And you'll notice, especially if you were in my 1010 class, please make sure you're careful on something like this. With subtraction, you need to make sure that that numerator is in parentheses because you better make sure that you distribute through correctly. So here's what we end up with. we end up with x minus 4 on the bottom, and then this is going to be minus an x plus a 4. So I have x minus x, that's a 0. And I have 2 plus 4, that's a 6. That's what we're after. Now, the interesting part on this problem is, this is a little bit unique. Clayton, what are we going to multiply by now? X minus 4 quantity squared. So when I multiply, I'm multiplying by a positive. I don't have to switch the direction. It is going to cancel off that x minus 4, so that's going to leave me with a 6 and an x minus 4. Now take a good look at that. What's the x-intercept? The x-intercept is 4. Whoops, positive 4. Yeah, you could. Yeah. And what does it look like? Looks like 6x. So it looks like this, right? Pretend that went through that point. And we want to know where that line is. Greater than or equal to 0. Where is that? So that's going to be from 4 to infinity.
So problems like that,
No, in general, this is a pretty easy one, but there's still, thank you, I have 2 hands up. Anybody else want to raise their hand? Parker.
Oh.
Very good. Okay, see how easy a habit this is to get into, and see why it would be better whenever you have a domain issue, point that out to begin with. So if right here we said, hey, you know what, I can't have x equal 4. When I get done here, I say, wait a minute, even though this is saying when is this line above or on the x-axis, and that is from 4 to infinity, this isn't the original graph. It's a really ugly graph to begin with. It's got horizontal asymptotes and vertical asymptotes. We changed it into this form so it was easy, but we want to make sure that we don't include something that's not in the domain. See why you need to be careful with that? Okay, thank you very much. Any other questions on that one? Christopher.
When you got to the second, like when you had subtracted 1, couldn't you times the whole thing by x minus 4 squared and do it that way?
So let's see what happens if we do that. So if we had x plus 2 over x minus 4, and then this was minus 1 greater than or equal to 0. Christopher's suggestion right there is to multiply this whole thing by x plus 4 quantity squared. So that gives us x plus 4 times x plus 2. And when I multiply here, that's going to be minus x plus 4 quantity squared greater than or equal to 0. Right? Then you have to multiply these together, multiply those together, collect like terms. You're going to end up in the same place. I think it's usually just a little bit easier to do it that way. It's personal preference. There are lots of different approaches to this. You could solve this using a sign line if you wanted to.
I'd rather not.
Yeah.
X minus 4 squared? Do you have to change the sign?
Yeah, this is a minus. Thanks. Good. Okay. Anything else? Okay. And if you had a different teacher, they might show you a different way to do it. I think turning these into polynomials that we can graph, I think those by far are the easiest way to go. Okay? All right. So go ahead and solve this problem right here.
You have to solve it or just tell you how to be in this place?
No, I want you to solve it. I want you to finish it. And then stop whining too. Okay, before we get too far, let's kind of figure out the ideas. Ideas on how to solve this. Zach.
Well, I would just, set the equals 0, so I'd move the 3 over x plus 1 to the other side.
Okay, so option 1 would be to start it like this. Does subtracting this to this side, does that change the direction of the inequality? No. Okay. Any other ideas? Could we cross multiply? Could I multiply this? So could I multiply like that? Those are called cross products. Could I do that? Answer to that is no. Can somebody tell me why you can't do that? We could do something like that, but we can't do that.
What?
You,
Yeah.
well, it would be if they were equal to each other. It would be a proportion. And then there's another problem. You don't know whether what you're multiplying by. So on this side, we're multiplying by x plus 1. And on this side, we're multiplying by x minus 3. You don't know whether those are positive or negative. Okay. The other equivalent to that would be, what if I were to multiply everything by x plus 1 quantity squared and x minus 3 quantity squared? That would do it. But then look how many factors you're dealing with. Okay. Can anybody think of another way to do it? Yeah.
So now that you have the it's set equal to 0, you need to get a common denominator.
Okay, we do, but can anybody think of another way to approach this? This would work, but you're going to have lots and lots of multiplication to do and lots of factors to deal with. So it would work, it's just going to be fairly lengthy. Can anybody think of another way? Yeah.
Well, I don't know if this is right, but I just times the left side by x plus 1 and then the other side by x plus 3. Can you just do it that way?
No, because then you're multiplying, you're multiplying by a different thing on each side, so that's not good algebraically, and you don't know whether what you're multiplying by is positive or negative, so that wouldn't be okay. Those are really the two approaches. That's really what you're stuck with, and this one's going to be pretty long. Lots of algebra to get there. This is, what next, Tylin? Now get a common denominator. So this is going to be 5x plus 1 minus 3, put this in parentheses, x minus 3 all over x minus 3, x plus 1, and that's still greater than 0.
I have a question.
Yeah.
Do you have to times it by them squared, or can you just times it to the
No, you have to multiply them by them squared. Okay. So this is going to be, let's see, we've got a 5x plus a 5 and a minus 3x plus a 9. So that's going to be 2x plus 14. Is that right? Okay. So I've got 2x plus 14 over x minus 3, x plus 1, greater than 0. Okay, now at this point, we haven't done this yet, but I'm hoping somebody on their paper said, hey, wait a minute, he said we ought to be really careful if these are rational expressions. What do you need to throw out?
3 and
Yeah, you know for a fact that the answers cannot possibly contain 3 and negative 1, okay? So at this point right here, that is the next step that you'd take. You'd multiply by x minus 3 squared and x plus 1 squared. But you'll notice this isn't too terribly bad because one of the x minus 3's cancel. That leaves an x minus 3. One of the x plus 1's cancel. So that leaves an x plus 1. And then we've got, help me out here, I would probably pull the 2 out and leave this as an x plus 7. And then can you graph that? Sure. And it looks like 2x to the third. Okay? And then you're just looking for where the graph is greater than 0. The domain issues aren't going to be that big a deal because they're not going to be included anyway, but that's the idea. Generally speaking, a lot better than using a sign line to solve those. Okay? You've asked some very good questions today. That's nice. You're thinking. Okay? Any other questions?
On our
Yep.
homework, is it going to tell us that we have to use either the graph method or the sign line, or does it just say solve?
It'll say solve, and I'll tell you right now, I'll take I'll take either of those on the test. Again, the nice thing about this is, I mean, even on this ugly problem right here, that's really not that much work to show, and you get to a point where you're graphing a polynomial. I mean, it's good practice for what we've already know how to do. Okay. All right. Any questions? We're going to turn in 5.2 and 5.3 tomorrow. If you've got questions on those, make sure you come see me and ask. If you want to stick around after right now and ask me, that would be fine. I will show you both those quizzes tomorrow. We'll take a look at those, and I'll show you what you got on them. All right.